Today we're going to be looking at how objects can undergo circular motion under the influence of gravity. So the simplest scenario that we could discuss this is like a satellite orbiting a planet like the Earth. So in this case, the centripetal force acting on this body is equal to the force due to gravity. The resultant force on this body is the gravitational force exerted on it by the planet. And this is the resultant force that acts towards the center of the planet. And therefore, given that it is traveling with a velocity v that is perpendicular to this gravitational force, it will travel in a circular path. So we know that the equation for the gravitational force is equal to gmm over r squared. And we know that our equation for the centripetal force is mv squared over r. So we can here actually work out the orbital velocity of this object. Now the first thing that you can notice is that the masses of the satellite cancel. So this already tells us that the orbital velocity is independent of the mass of the satellite. And if you do some more cancelling and some rearranging, we get that the orbital velocity is equal to gm over r, where r is the distance between the planet and the satellite. So if we were to find out the kinetic energy of this object, well, we know that kinetic energy is obviously half mv squared, and v squared in this case is gm over r, so we would get that the kinetic energy is equal to gm m over 2r. And we know that the gravitational potential energy of this satellite is going to be equal to minus gmm over r. And remember that in the last video we said that the negative sign of the gravitational potential energy is important. So for objects that are undergoing circular orbits around a planet or a star, the total energy is obviously going to be equal to the kinetic energy plus the gravitational potential energy. And this is given by gmm over 2r minus gmm over r. And this is equal to minus gmm over 2r. And we can see that this is basically equal to minus the kinetic energy. So for a circular orbit, the total energy is equal to the negative of the kinetic energy of the satellite. And this means for circular orbits, the gravitational potential energy actually doesn't have an effect on the total energy of the satellite orbiting. But you have to be very careful, and you have to understand that this is for circular orbits only. Now we're going to look at the derivation for Kepler's third law. So let's look at a planet orbiting a bigger star. So let's look at the Sun and the Earth. Now Kepler's third law allows us to work out the time periods of different planets orbiting the same star simply by looking at the radius of the orbit. So we know that the gravitational force is equal to the centripetal force. We know that the gravitational force is gmm over r squared. But this time we're going to say that the centripetal force is equal to m omega squared r. Because as I said, we're going to this time look at the time period of these orbits. Again, we can do some cancelling. And we know that omega is equal to 2 pi over t. So we do that squared times r. Now if I multiply both sides by this r squared, we get gm is equal to 4 pi squared over t squared r cubed. And then if I times both sides by t squared and divide by gm, we can see that t squared is equal to 4 pi squared over gm times r cubed. You can see here for the same star, this part here is constant. So we can say that t squared is directly proportional to r cubed. And this fact here is what is known as Kepler's third law. Now the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.